Okay, so this is a business which is trying to capitalize on deep fakes in an honest way. How do you capitalize on deep fakes in an honest way, you might ask? Well, I'd like your impressions of this before we start in. So let me go ahead and share my screen. And okay, here it is. Now, the interesting thing is I think that any of you, given a little bit of time, could do this same business. What they do is they generate kind of abstract art using, I suspect they use GANs, and they sell them. Now, where would you sell these to? There was a Sotheby's auction for one of the first AI generated portraits, something called Bellamy or something like that. We covered it in the class, but it sold for $475,000, almost $500,000 at an auction of Sotheby. Not because it was great art, but it was probably the first art that was actually reduced to canvas in using artificial intelligence. So it has that distinction. These are more easily generated pictures, and you can purchase them, and they come framed, and they're very nice and they're very high resolution. I understand. I want to order one just to see what it looks like. But here are some things. You can look at these different designs, and I'm going to click, and you can see some of the different designs here. I don't know. Mark? Yeah.
We just see your email. Are you trying to show us something?
You're showing me my email. Oh my goodness. This is not good. Okay. You've seen all my dirty laundry now, right? And it's captured for posterity. Okay, I grabbed the wrong screen. Let's see if I can do it right this time. Here we go. Thank you for letting me know. Do you see it now? Okay. Well, what do you think of this? What's the impression that you get? I don't know, something kind of maybe bordering on satanic, right? Kind of an evil spirit. Here's another one. This is kind of nice. It's kind of a surrealistic depiction of little children in an island, and each one is very different. This one looks like a little bit of soft porn might be in that, depending on your imagination. And you keep clicking on this, and you get all of these very interesting sort of portraits. This art, where you can purchase this art, and it's sent to you in a nice frameable format. And it's just more than the deep fakes, but it's also the presentation. The bells and whistles are sometimes just as important as some of the other stuff. This reminds me, I'm going to give you my impressions. This reminds me of 1984, kind of a dystopian future, right? Where everything is going bad. I have no idea what this means. It looks like it's in some Latin or something like that. I'm sure that those words mean nothing. This also reminds me of a dystopian future and maybe a scene from Blade Runner, right? Oh, this is kind of sad. You're thinking of starving children, possibly after the defeat in World War II, right? And starving Europe, and these kids are in need of food and an abstraction. This is this might be a consequence of global warming, I think, right? All the dams have bursted. There's flooding everywhere. I don't know. I'm not a big fan of this. This might be the new Russian hypersonic missile that everybody is talking about, and it's breaking the sound barrier. This looks to be a strange science fiction sort of thing. Maybe zombies. I'm doing this, by the way. I haven't seen these before. I'm just giving you my initial reaction. This one looks like a very zombie-looking baby woman that's giving childbirth. Those are Russian eggs. Anyway, looking at these, and they can be purchased in final framed format for about $40 or something like that. My goodness, this one looks like, does that look like a Monet? I'm not very familiar with different objects, or different painters and different styles, but they kind of looks like a Monet, doesn't it? I'd be interested in any of your thoughts on this. And I'm going to give you my overall impression of these, but I'd like to hear what you say. This is not engineering. This is arty sort of stuff. So do you see any there that you would buy for $40? Why would you buy something like this for $40? Just on the, I can imagine, for example, just hanging on hotel walls. Hotel rooms would put stuff like this up, I would imagine. Whoa, this looks like something from Star Trek or Star Wars in the future. Anyway, any thoughts on this?
Was there any specification of what model they actually use?
You know, I don't know. I'm going to call up this guy and I'm going to talk to him. I told him in my email, I suspected they used it again, but the diversity of all of these suspects that gives me the suspicion that they use a number of different GANs trained on different motifs, if you will. That's my hunch. I don't know. But the variety that's available is really interesting. But again, I suspect that any of you, given the business background and the business, reminds me of a cult. That any of you with a background and the access to these things such as PyTorch and TensorFlow and some of the more sophisticated training could generate this business also. I don't think I would buy that one. I don't know what it is. So anyway, any thoughts? This is not a test or anything. I just wonder what your impression is. And do you think this business will be successful?
I think it could be.
What's that, Trevor? You think it'd be?
Yeah, I mean, there's plenty of places that are just looking for random art to put up. And if this can generate art of this quality, and I don't know how long it takes to generate a piece like this, but I assume that it would take less time overall than it would be someone actually thinking of this and then painting it. They'd be able to churn it out at such a fast rate that people would buy this up very quickly.
Yeah, and the thing is, you can click on this thing forever and get such a diversity of different products. So is anybody, does this solve anybody's Christmas shopping problems? Not mine. I think I might buy one of these just to see what it does. But I thought I would show you this because this might be something which you see on hotel rooms where they hang up the art above the bed and things of that sort. Okay. So was that interesting? It was. And that's one of the questions I'm going to ask you in the final examination, which I wanted to address before we got into the presentations, is number one, where do you see a reduction to practice? Now, what is a reduction to practice? That means that it lives more than on a journal page, because I have been around long enough to see so many papers, so many hyped concepts being hyped on journal pages that don't survive. They don't survive because they're not reduced to practice. They are not generating a value added component to the state of the art, and therefore they kind of fizzle out. And I'm wondering about this. We talked about in the beginning with the hype curves. You remember the hype curve way in the beginning? There was kind of a hype. There was a undershoot of disappointment, and then there was the asymptote of reality, wherein there were things reduced to practice. And I think we all see applications of a lot of these, but I would like to know where you see these applications in the future. And not just Yeah, I'd just like to get your idea of where you think this technology is going, because we can spend a lot of time doing things like studying these things. I mean, I have wasted a lot of time teaching a class like this before, where we talked about things such as content addressable memories and Hopfield artificial neural networks, and BAMs, bipolar associative memories. And it turns out that all of those have bit the dust, because when they were scrutinized, they just didn't stand up to, they either didn't stand up to the technology that existed, or there simply wasn't a market for it. There was no place for the reduction to practice. And as engineers, we need to think about this. This is above and beyond the glitzy sort of stuff. So with that, let me try to see if I can successfully share my screen with you again, and without you seeing my dirty laundry in my email. Yeah, there it is. Okay. So hopefully now you see the spreadsheet. You see the spreadsheet? Okay. Now this is on Google Docs, and you might not notice it, but if you go to this tab down here on the left, you see this class notes. You'll recognize this is where we put all of the stuff. So I have all of the stuff for the course. So you can see we've covered quite a bit of things here. And there's another tab here, final notes. And this is what I want to talk to you about on the final examination. The final examination is, I'm going to be spending 30 minutes with each one of you, and we'll schedule that. We want to talk about that in a second. But this is kind of a more detailed outline of some of the things that, we'd like to talk about. Just interestingly, I'm not interested in the memorization of formulas, because anybody can go look up a formula. I think a successful class is one where you come out and you have this concept of a toolbox full of applications. And in your engineering practice, you come up to this, you come up to a problem, you say, oh gosh, I saw this. What was that? But, oh, simulated annealing. I think we might apply simulated annealing there, because I remember that in the class I have. And then you could go look it up. You could go look up the details. You could go look up the mathematics. So I'm more interested in you coming out of here with those sort of concepts. But you can see these are different topics that I might ask you in terms of the final examination. We covered swarm intelligence, as you can see here at the top. Ants, termites, gnats, birds. Some of the applications, particle swarm search, I think is a big one. It's particle swarm search kind of doesn't belong here, but a lot of people call this swarm intelligence, so we'll include this. You remember the particle swarm search, which is the way that search was achieved using flying birds. And then we'll use regular search and talk about multi-agent computation, search types, search types. Okay. For example, the idea of multi-agent search, evolutionary search, steepest descent, and things of that sort. I'm interested in the no free lunch theorems and what needs to be bought towards the search. And I'm talking about domain expertise and the generation of active information, and that addresses the conservation of information and the use of active information. We spent some time on fuzzy systems, and here is an overview of all of the different aspects of fuzzy systems. And this disjunctive versus conjunctive reasoning down here is the same thing as the Combs control. So maybe I should even put Combs there. Then we'll talk about training, the foundations of pattern classification and regression. We did talk about the Fisher distance and branch and bound. This is kind of a classical linear approach. And as you saw in support vector machines, that many times one can get a very nonlinear problem down to a linear classification problem by increasing the dimensions of what goes on. I'd like to talk about inversion, error back propagation, which I think is, as you heard from the interview with Paul Werbos, is probably one of the most widespread of all algorithms in engineering right now. It's being used probably 1,000, 1,500 times right now in terms of training. The idea of convolutional neural networks, simulated annealing, particle swarm. This is a little bit redundant because we had particle swarm up here also, and the concept of the autoencoder. And then the other things, the limitations of AI, we talked quite a bit about the limitations of AI, and I'm interested in your thoughts on that. Specifically, the active information. This belongs up here with conservation of information. Things such as GANs. I didn't find an interesting place to put GANs, so I just put it on other. The questions that I will ask you also is which was in your mind the best paper presentation of the 6 paper presentations that we have, and whoever gets the majority vote there will get some, I don't know, a little bit of extra credit. And the other places, where has deep learning been profitably reduced to practice? And I would stay away from things such as delayed scrutiny, where people say, well, you know, this really has promise, and in 5 years we'll be able to apply it to such and such, or in 10 years we'll be able to apply it to such and such. It turns out that research is always full of these delayed scrutiny claims that, excuse me, once you get down the road a little bit, you find out that they're totally empty. And so it's very easy to have this delayed scrutiny, and many times this delayed scrutiny turns out to be without foundation. And I will mention that in the publicizing of some of my research, I have appealed to delayed scrutiny, and I have appealed to delayed scrutiny which had no fruit at the end. So it was a totally bad prophecy. And if you follow biblical prophecy, you know that if there's prophets in the Old Testament that gave bad prophecies, sometimes they were punished pretty bad, including murder, being executed. So with that, any questions on the overview of what's happening here?
Quick question. Are you just going to ask general concepts?
Yes, my questions will be in general concepts. Okay. Like I might ask, for example, what is a fuzzy set? Okay, hopefully you should have that in mind, very solid. What do we mean by fuzzy inference? Fuzzy inference, by the way, is kind of the same thing as Mamdani control, and also disjunctive reasoning, and how these things work. So the questions will be very general, and I will ask you generally how things work. I will talk about, for example, what is a convolutional neural network? Explain me in general the architecture of a convolutional neural network. Or error backpropagation. Explain to me what error backpropagation is. I don't want the mathematics, but I do want something that talks about the error backpropagation and why it's so important. And the reason, of course, this is so important is that localized sort of update that one can do, as opposed to looking at the entire neural network and updating all of the weights according to a global knowledge of what is going on. Rather, the updates can be done from neuron to neuron by the forward and the backward error propagation. I might ask you, what is simulated annealing? Explain it to me in general terms. Okay. So those are the sort of questions that I will be asking. You're welcome to have notes. What I would suggest to you is that in studying for this, you go over the material and you make yourself out an equivalent of maybe 1, 2, or 3 pages of notes from the course that you can refer to. And I have found, when I used to take classes, that was a good way to prep for an examination, because it forces study and focus on this. Okay, if there's no questions, then the thing I would like to ask next is, when would you like to have the finals? We can do them Thursday, Friday, or Monday. Does anybody have any druthers? Number 1. Number 2, do you know what druthers means?
Do you mean the Thursday and Friday later this week?
Well, let's talk about it. Yeah, I was thinking in 2 days, 3 days, or 6 days, or we could do it next week. I mean, that's fine with me. Does anybody know offhand when our final examination is scheduled?
I think it's scheduled on originally a Saturday, 4:30. That's what I have written down.
Okay, this coming Saturday. Okay, which would not, I'd prefer not to have it on Saturday, but if we could do it on a Friday or a Monday, that would be good.
Yeah, the Thursday was feeling a little close, like 2
Okay.
days, a little more than that. So Friday or Monday would work for me.
Okay, well, let me choose Monday. Does anybody have any?
I have another final in Monday.
What time is your final?
It's from 1 p.m. to 4 p.m.
And what is the class?
The power system.
Power systems.
I have a final exam on Monday as well at 4:30.
Okay, let me ask you this. Does anybody have a final examination on Friday?
I believe Friday or Thursday and Friday were scheduled as the university study days for finals.
I understand. So let me
Yeah.
ask the question again.
So,
I guess
don't-
nobody has
Yeah.
this.
I think if that's the case, no one has Friday.
So my question is would you rather keep your Saturdays free as I would, or would you rather? I'll give the examinations on Saturday if you want to.
Friday works for me.
Friday works for you? Okay.
Is Monday the only day next week that you're available, Dr. Marks?
No. We could do next Tuesday if you want to too. That'd be fine. Next Wednesday is out though.
I could do next Tuesday.
Okay, anybody have any objection to next Tuesday then? Okay, so that's it. Good. We have consensus then. So what I'll do is I'll put out a spreadsheet, a Google spreadsheet, and you can sign up for whenever you would like. If for some reason you can't make it, let me know and we'll make alternate arrangements then. Okay. Okay, with that, let's go ahead and start the presentations. And Min-Kun, you were called on last time, but you weren't ready. So let's start with you. And I am not going to put up the title of your paper and stuff, so I'm going to let you introduce your own paper, okay?
Okay. Can I share my screen?
Yes, you can. The question is will I let you? Okay, thank you. You're good now.
Can you see my screen?
Yes.
Okay. Today I would like to introduce the paper whose topic is adversarial distributional training for robust deep learning. So first of all, let me talk about the robust deep learning. So suppose we have a deep neural network, and we have which is a classifier, and we have the natural input, and without the perturbation, and it can accurately classify the atoms. But if we add a small amount of the perturbation, even a small amount of the perturbation, and as a human, we will not recognize the difference between the natural input and the image with the perturbation. But for the model, it may make a misclassification for the input as another kinds of the atoms. So this means that our model was attacked. And so in this case, if we have other kinds of the application for the deep neural network model, and if our model is attacked, so this will cause some security problem. So the need for the robust deep learning. So the approach for robust deep learning is demanded. And in a few recent years, there's an approach called adversarial training was proposed and developed. And the adversarial training was used to improving the model robustness of the deep neural networks by adding training data with adversarial examples. So it is actually formulated as a minimax optimization problem. We can see that the inner maximization aims to find an adversarial examples that maximize the classification loss, and the outer minimization aims to train a robust classifier using the generated adversarial examples. So actually, the method of adversarial training or AT is actually to for the inner maximization is going to find the perturbation, to find the perturbation set, and then it generates a perturbation set, and it is trained and it is trained by the deep neural network. So it is basically so it is based on the adversarial examples, and recently the AT is very popular used for the robust deep learning. There's some problem of AT as introduced in this paper. It solves the inner maximization problem based on specific attack algorithm, which is vulnerable for other unseen attack under the same threat model. And a single attack algorithm could be insufficient to explore the space of the possible perturbations. So actually, the problem of the AT is just going to find the set of the adversarial examples. And this kind of the adversarial examples, there may be, if we just change it a little bit, so it may not recognize the kinds of the adversarial example, so it will still have another attack. For example, if we have one adversarial model and it can survive in one attack model, but in other kinds of model, it may not survive. So under these conditions, in this paper, an approach called adversarial distributional training, or ADT, is proposed. So actually, ADT is an improved version of AT, similar to AT. It is also formulated as a minimax problem. But the main difference is the inner maximization. The inner maximization of the ADT aims to find an adversarial distribution for each natural example by maximizing the expected loss over the distribution. So actually, instead of instead of finding the examples, the adversarial examples, it just find the adversarial distribution for each of the natural examples. And after finding the distribution, the best distribution, and then we will apply it to update the parameter of the deep neural network using the outer minimization formula. And just a note that we need to notice that AT is a special case of ADT, because if we keep our distribution density function as a direct delta function, and it is no longer the distribution, it is just an example. So the ADT will finally degenerate to AT.
Min-Kun, where is this distribution taken? Is it taken at the, where is the distribution? Is this the distribution of the input, distribution of the output? Is this something you're going to show us here?
The distribution is for each natural example. That's for the that's kind of the distribution is for the perturbation set. And actually, I would like to show you the mathematical form of the AT and the ADT. So if we look at the so let me introduce the mathematical form first. And so the mathematical form, we have the delta I. Delta I is actually the set of the perturbation. The set of perturbation. So actually, if the AT is going to find the optimal perturbation, maximum perturbation using the loss function, and the ADT is going to find the best probability density function of the perturbation. So actually, this distribution is actually for the perturbation part of this ADT training. And the difference between the ADT and the AT is that the ADT used calculate the the maximum of the expectation value of the loss function, the expectation value of the loss function, and then update update the probability distribution instead of the perturbation set. But if we compare with these two form of these two mathematical form, we can see some similarity, and we can get one relationship. The relationship.
Could you go back, please, one slide? What is, I don't understand what the script L is, what the F theta is. You have a number of things you're not defining here.
Okay. Let me introduce it. So actually, what is F? F is actually our deep neural network model, and we have the parameter theta. We have the parameter theta here, and we have the input xi. Xi is our natural input. For example, our image without the noise, without the perturbation, and we add the delta I. Delta I is the perturbation set. So we add the input of our data and plus the noise. And yi is actually the thing that we need to classify. So L is the loss function of this deep neural network, and we are going to find the maximization of the loss function. We need to find the optimal perturbation set theta I, and then we use the auto minimization to update our theta.
Okay, I missed. What is the script L again?
Oh, sorry.
The script L.
L is the loss function.
The loss function. Okay,
yeah,
thank you.
Function. Okay, yeah, and we update our theta. So here's the cycle. We use our inner maximization of the loss function to update our delta I, and use the outer minimization to update our theta. The theta is the parameter of the deep neural network model. And actually, these two, the ADT is similar to the AT, but what we are going to calculate the expectation of the loss function. And then we are looking for using the inner maximization to find the best distribution. Best distribution corresponds to delta I, and using the outer minimization to update our theta. Again, the theta is the parameter of our deep neural network. So as we compare with the inner maximization of AT and ADT, we can notice that the maximum of the expectation of the loss function is actually smaller than the maximization of the loss function. And I think this is not difficult to understand because the expectation is taking the mean value. And if we are looking for the maximization of the mean value and looking for the best distribution, and the largest mean value is absolutely smaller than the loss function.
So with that, first of all, I think you've misspelled Dirac. I think it's AC, but
which one?
The Dirac delta.
Yeah, Dirac delta.
Okay, that's small thing.
Okay.
So how do you choose the distribution for the del sub i's? Do you choose a certain probability density function class, or what do you choose?
Yeah, I will introduce in
you'll do that. Okay, thank you.
Yeah, I'll introduce in the later. Yeah, this is the general form. So actually we know that the expectation is smaller than the loss functions, and this indicates that the optimal distribution by solving the inner problem of ATT will degenerate to Dirac delta function. So ADT become AT, and this is what we don't want. We still want our ADT. And in order to solve this issue, so the paper just add an entropy regularization term. So the minimax expression becomes in these forms. So we just replace our max with the function of J corresponding to the distribution of delta I and the theta. And J is actually the objective function. The objective function is actually the expectation of the loss function plus this entropic regularization terms, the nominal multiplied by the H, and the H is actually the entropy of the probability density function of delta I. So this is the way that the paper solved the problem that not letting the ADT degenerate to AT.
Okay, is the lambda a Lagrange multiplier, or is that a parameter that you choose when training?
Yeah.
No, that was not a yes or no question. Lambda is either a Lagrange multiplier or it's a parameter you use in training.
I think yeah, I think that's the parameter that they choose. They choose from a range of the this is not for the training. This is this coefficient that they select. I don't know
this is for what? It's not for the training. It's for what?
This is not for the training. This is the value that they select this value. So they also compare with the impact of the lambda. They see the effect of with different lambda and the robustness. They compare with the robustness. So the number is what they train. I don't know the exactly the term how to say it, but that's the coefficient is not trained.
Okay, thank you.
Okay. And so in this page, I would like to discuss about the superiority of ADT. So as the previous introduction, we have already known the difference between AT and the ADT. And AT actually finds the worst case adversarial example, while ADT learns the worst case adversarial distribution comprising a variety of adversarial examples. So actually, adversarial examples can be generated by a variety of attacks. And we expected that those adversarial examples probably lie in the region. So that should be in the region where the adversarial distribution has a high probability, such that minimizing the expected loss over the distribution can naturally lead to a better generalization ability of the trained classifier across the attack under the same threat model. And furthermore, as we add entropy regularization terms into the objective function, the adversarial distribution is able to better explore the space of possible perturbations and categorize diverse adversarial examples compared with a single attack method. So actually, for the approach of AT, they are actually training the adversarial examples. So actually, if we make a slightly change of the adversarial examples, it is still a noise, but the model cannot recognize it is another noise. So it will have the probability that under one attack model, this deep neural network can provide high accuracy, but in other kinds of the model, it will provide low accuracy. But for ADT, maybe in one model, it can provide high accuracy. In another model, the accuracy will drop a little bit, but it is not drop dramatically as the AT. And this is the general algorithm for ADT. And we have our the training data. The training data is actually xi, yi, and the objective function that we have already derived. That is the expectation of the loss plus the entropy term. And we have the set of the distribution. The distribution is corresponding to the perturbation set. And we have the learning rate. And so first of all, we can just obtain the best our best distribution by searching for the best distribution using the objective function. And after we have the best distribution, and we can update our theta. The theta, again, the theta is the model of the deep neural network with the gradient descent method. We have the learning unit and then calculate the expectation of the gradient corresponds to the theta of the objective function. And so I can update our probability density function and the theta step by step using this general algorithm for ADT. And this is the model that they develop as answering your question about what kinds of the distribution that they are using. So first of all, the first model is called the ADT explicit. So actually they are using the explicit modeling of the adversarial perturbations. Actually in this paper, they are just using the Gaussian distribution. So in this case, they just so how they choose the best distribution? They choose the best distribution using the parameter like the mean value and the standard deviation value because assume the distribution is explicit. So they use this value to update. For each of the distribution, they update their mean value and the standard deviation, and then update the theta. So this is the one model is explicit model. And the next part is the how to spell it? More amortizing the explicit adversarial distributions. So this is this is a model that in response corresponds to the explicit model. We still have the explicit model, but in this way, we have our natural input. We have our actual input, and we have a mapping. We have a mapping to the distribution, the probability density distribution, and using our natural input to output the parameter like the mean value and the standard deviation value. So actually, this way, they use the probability density function is a conditional, in a conditional manner, rather than just the probability density function of delta I. The third one is the implicit model. So if we don't have a explicit model like the Gaussian, distribution, so what we should do, and I will just introduce these three models step by step. So first of all, this is the explicit model for the ADT. So here's to model the adversarial perturbation around an input data using a distribution with an explicit density function. So delta I, we recall is the perturbation set is actually in this form, using a small amount of the if genome multiplied by the hyperbolic tangent of UI, and UI is correspond to the Gaussian distribution with the mean value mu I and the standard deviation of a set of the sigma I, and we class the mu I and the sigma I as phi I. So when we redo our inner maximization formula, we just what we need to update for each step, we just need to update our phi I. Phi is the mu I and the sigma I. And then they just parameterize delta I in this form. So they just replace UI as a mu I plus the sigma I multiplied by R. And the R is an accelerating noise variable following the standard Gaussian distribution. So if we put everything into the so we need to calculate the gradient of corresponding to the theta I, because we need to update the theta I, and we got this formula. So for each of the step, we need to update our theta, which is mu I, and theta I, and produce delta I. And the next part is the amortizing the explicit adversarial distributions. So why they propose this method? Because they actually realize that the explicit ADT needs to learn the distribution parameters for each input, and then brings prohibitive computational costs. So the method of this amortizing the inner optimization of ADT explicit is proposed. And they just define the adversarial distribution for each input in a conditional manner. So similar to the previous maximization, inner maximization form. What they replace is to replace all the probability density as a conditional manner, the delta I in the conditional of xi. And here we have so this picture is how the theta is generated. So actually here we have the xi as an input, and with the mapping is actually from input xi to the distribution density function. So we have the input, and then it will produce the mu I and the delta I. And similarly, we add this R and then produce our delta I. And in this way, the generator network can potentially learn common structures of the adversarial perturbations, and which can generalize to other training samples. So what does it mean? It means that there's no need to optimize the phi, excessively on each data xi, which can accelerate the training. And the third model is called the implicit model, implicit model of adversarial distributions. And the paper also saying that sometimes it's harder to specify a proper explicit distribution of adversarial examples, which may lead to an underfitting problem. So they need to develop the model for the implicit distribution. So first of all, they just learn a generator. So the generator G5 is actually we have two sets of the data. one is DZ and one is RD, and then they need to output one data set. So this is how it works. So we have delta I equals to the mapping of G5. We have a Z and XI, and then it calculates delta I. So one thing it is not known is Z. Actually, Z is need to sample from the uniform distribution based on the prior distribution correspond to Z. They have the PZ using the uniform distribution. So we know what Z is, and but the next hard part is that the entropy of the implicit distribution cannot be estimated exactly, as we have no access to the density of the probability of the conditional conditional probability density function, because we don't know the distribution, so we don't know what the distribution is, and the authors just develop a method. They just instead maximizing the variational lower bound of the entropy. So in their appendix, they just have the proof of this entropy term larger than this value, and Q is the introduced variational distribution. So finally, what they can get is in this min-max form. So we can have all the stop nodes. And if you are interested in this, all about these mathematical forms, how they are derived, how this kind of the inequality is derived, you can just go to refer to the appendix of the paper. So these are the three methods, three model of the ADT. And the next part is they want to compare the robustness between the existing AT models and the ADT model that they propose. So we have 1, 2, 3. We have 6 AT models here. We have our ADT models, our ADT model at the bottom, which is proposed in this paper. And the first row here means the different kinds of the white box attacks, and the last column is the overall robustness evaluation. Overall robustness evaluation. So how this is what's the formula of this? So the overall robustness evaluation is calculated in this formula. So we know that we have the AXI. AXI is the adversarial example given by attack A, and we have our indicator function. And we know that the indicator function is actually if it is belongs to A, it will output 1. And if it is not belongs to A, it will output 0. So with different kinds of the 0, 1, 0, 1 added together, and we are divided by the total number of tests, we can calculate the overall accuracy. And this kind of accuracy is calculated as the robustness evaluation. And actually here, from this formula, we can see that there's a minimum here. So generally speaking, the overall robustness evaluation is the worst case of the classification accuracy. And if we pick one AT model and one ADT model as an example, if we pick the standard AT model, standard one, we can see in the first white box attacks, the accuracy can reach to 94.81%. But at the second one, it can only reach to 12.05%. In other kinds of attack, there's no accuracy. The accuracy is 0. But if we looking at the ADT model, at the first attack, the accuracy can reach to 86.89%, and the worst case it can still goes to 50%. So there's about more than about 30% of the difference. But compared with the AT model, the difference of the ADT model is much smaller. And if we are consider the overall robustness evaluation, and we can see that the ADT model is the robustness of the ADT model is better than all of the other AT models. And another thing to be noticed is that the best case of the AT model is actually AT-PGD. The AT-PGD can actually produce the overall robustness about 48.26%. So in the next comparison, the author just picked the best AT model and the standard AT model as representatives of the AT model and compare with the ADT model. And this is the robustness under the white box test. And with the data is CRFAR10. The next part is also the robustness under the white box test, but they just changed their data set is to be CRFAR100 and SVHN. And using the standard AT model and the PGD AT model and compare with our ADT model, we can still, when we are looking at the overall robustness, we can still see that our ADT model have better robustness over other kinds of the AT models. The next part is about the black box attacks. So the paper just introduced the two kinds of the black box attacks. And for the first part, when we are looking at the accuracy, we are looking at the diagonals of it because.
Min-Kun, could I ask you how much longer is your presentation? Because we have two more coming up, and I.
Oh, okay. I think
you're just about done. Okay, good.
Yeah. Okay, I'll briefly talk about it. So actually, in generally, under the black box attacks, we can still notice that the accuracy, the overall accuracy is better than the ADT model. And another part is the additional study. One is the impact of lambda. As I said, this is not the trend data. This is the variable that we choose. So generally, a larger lambda leads to a larger entropy and better robustness. But if we have a too large lambda, we reduce the robustness. And the next part is that the author also wants to get some insight of why the ADT model experiences higher robustness over the AT model. So if we're looking at the loss surface of the AT model and the ADT model, we can see that the method trained by the ADT experiences smoother and more flattened loss surface than the standard and than the AT PGT model. So in this way, it can have better robustness. And another thing is that if we're looking at the dominant eigenvalues, actually the dominant eigenvalues are the standard derivative of these two of the models, and we can see the ADT model have smaller standard deviation. So it also means that the ADT model is smoother and shows better robustness.
What are the coordinates here of your fitness landscape? I mean, you're dealing with a very high dimensional problem. So how can you have just this two-dimensional plot of the fitness landscape? I don't understand where that comes from.
I think this is the. I think they are just showing that they're trying to explain this, and they are trying to visualize the loss surface in the vicinity of the input along the gradient direction. So what they see is this is the surface of the loss function. So what they see is the loss function of the ADT model, these three model, is smoother than these two model.
Okay, I'd still like to understand that, but go ahead.
Okay, so the summary. So I'll briefly talk about the summary. So actually, the paper introduced an adversarial distributional training framework for learning robust deep neural networks. So ADT can learn an adversarial distribution to characterize the heterogeneous adversarial examples from a natural one on the entropy regularizer. And in this paper, 3 ADT model is proposed with a comparison of the robustness of AT and ADT on the both white box and the black box tests. ADT is with better robustness than AT. And also, in this paper, they just claim themselves to be the first to train the robust model by learning the adversarial distribution. So actually, for me, I expected there would be more works on the ADT, and they can develop the ADT model so that we can increase the robustness of the deep neural network. Because actually, until now, the ADT is only a few percentage. The robustness is just a few percentage higher than the best AT model. So I expect there will be more ADT model to be developed to provide higher robustness. And thank you. This is my presentation.
Okay, any questions quickly? Let me ask. This was trained, for example, with the Gaussian sort of assumption of being adversarial. If you knew this, could you game this to beat that Gaussian?
So I'm talking about this one.
Yeah, I believe that you mentioned you used a Gaussian assumption for the perturbations. Yes. Is that right?
Yes.
Yeah. If I came along and I knew you were using Gaussian assumptions, is there a way I could game it and still kind of beat up your neural network from, say, a non-Gaussian perspective?
I think there's a the one explicit. I think this is the example that they use. They use the Gaussian as an explicit model, but they also use the implicit model for the adversarial perturbation, and the detail of the implicit model is actually there's no the distribution is not explicit, so we don't have the Gaussian distribution. So they are using this implicit model to generate this model.
Okay, thank you very much. Let's move on. Who would like to go next? Go ahead and unshare your screen, Ming-Kun, if you wouldn't mind.
Okay.
By the way, if you do have to leave, go ahead and leave. I'll stay here till the end. But if you do have to leave, you got to leave. So we're running really, really late here. So who would like to go next?
I'm last in the list, so I can.
Okay, go ahead, Matthew.
Oh, okay.
Or Innocent, if you want to go, you can. Or do you have... Okay. All right, I will share my screen. Oh, no, I opened the PowerPoint. I did not share the screen. I'm so sorry. And slideshow. There we go. Oh, that's my email. Here we go. All right, can you all see everything? All good, okay. All right, 3D R2N2. No, this is not a Star Wars character. This is a neural network. And what it is, it's a unified approach for single and multi-view 3D object reconstruction. And we'll get into what exactly that is in just a second. Here's what it stands for. 3-dimensional recurrent reconstruction neural network. And that is why they made it an acronym. It's a bit of a mouthful, but essentially the network learns a mapping from images of objects to their underlying 3D shapes. And so you have 3D shapes and you have images, and it learns the 3D shapes from those images. It takes one or more images and reconstructs a 3D occupancy grid. This is a 3D construction that, if you know the state-of-the-art stuff or even other neural networks, it doesn't take any image annotations and it doesn't take any class labels. So let's get into how that works. This is a standard neural network. I always like to start at the basics because I have limited understanding. You have a set number of inputs like these X's here. Ooh, do I have a laser? Nice, okay. For example, you have these X1, X2, X3. You have your vector of inputs and it just does a forward pass and you get your output. The thing with this is there's no memory. For example, if it learned a word, if it could learn a specific word in a sentence and learn to detect those, but there's no context to the word. Like, I love fudge brownies. The fudge means the same as in what the fudge. Obviously, they don't mean the same things. So, also, I'm going to denote all these X's, this array, as just one. So just assume whenever you see the input, make it an array. So what we need is a recurrent neural network, an RNN. And this isn't to the paper stuff yet. This is just some of my research that I learned. what it does, it introduces this time step, a time step t, for example. So if we have our input and it's got a output here, what we have is a hidden state, and the hidden state at time t is affected by the previous hidden state. And that's all what we mean by recurrent, is just something with some recurrence. But what we get from this is some kind of memory effect. This is how it would look drawn out. So at time equals 1, this is your neuron, so to speak. And then that changes at the next time step, and then the next, and it goes on, etc., like that. And so we have a memory now. Sweet. Long short-term memory, LSTM networks. So this is a type of recurrent neural network unit. It solves a problem from the previous RNN and makes it capable of learning long-term dependencies. Just a normal RNN, it has a trouble with long-term dependencies. And so this fixes that. And how it fixes that is it's got two states. It's got a hidden state, and it's got a cell state. It's got a hidden state and a cell state. This here is a hidden state, and this one's a cell state. And it controls how each gets updated by gates. So this is the previous hidden state, goes through what's called this forget gate. And this determines how much the cell forgets, or inversely remembers, of course. And then we also have the input gate, and this determines how much of the input, this X being the input, that feeds into our states. And then the output gate, that determines how much our output takes on the input and the states. At any point in time, this H of t, this hidden state, is what we call our output. And then this other one, this cell state right here, that's still hidden. It basically doesn't see the light of day till, ever.
Should that forget point be obvious? It isn't to me.
The forget?
Yeah. I think that's what you called it, isn't it?
Right, exactly. So it takes the input and the hidden state. It generates, so it takes these two inputs and it generates a value of zeros, or sorry, a vector of values from 0 to 1, and it multiplies that by the cell state. Essentially what it does is it determines how much of the previous cell state it remembers. Does that make more sense?
Yeah, okay, thank you.
And these little yellow boxes, oops, that was the up arrow. These are actually neural network layers in themselves. Because remember how we have an array of inputs, and those get mapped to an array of outputs. And notice that there's two vectors that go into here, but only one vector that comes out. It's a 2-to-1 ratio. So that's how it handles that. And each one of these nodes is just a plain simple neuron. All right, there's another version of an RNN. It's like a LSTM, but a little simpler, called the GRU, or the gated recurrent units. And you can read these equations if you like. I'll probably forget them. And so this is what it looks like. It's a little simpler. It only has a hidden state. It doesn't have the cell state, but it's still got some of these same gates. How the 3D R2N2 works is we take an image, it goes through a encoder, and what the encoder does is it does convolution and pools and convols and pools, just like our normal convolutional neural network, until it gets to the fully connected layer. Every feature in this fully connected layer goes to a 3D grid of these LSTM units. So imagine this is a 3D grid. And we have several layers of these features. And so every unit in here, every LSTM, it maps to a specific portion of the 3D occupancy grid. So this one in the upper left would match to this section in the upper left of the box that we're filling. Then to get the 3D image, it just decodes it using a 3D deconvolution via unpooling. And then of course, softmax activation function. And so if we do this several times, if we keep feeding it images, that's where the recurrency comes in, the recurrent neural network. And instead of giving a completely unique or new output every time we feed in a different image, it remembers the image from before. And so it starts off with a okay-ish 3D representation, and then the representation gets better because it has a concept of memory. Trevor's word processing, or the word generation, I believe that was an RNN, right? And so it used the same kind of concept of having this memory. This is the 3D R2N2. You can see that encoding layer, and then we have that grid of 3D long short-term memory units, and then it has the deconvolving layer. They have an alternate form that has these jumps. We won't get too much into the difference between these two, but these are basically their two main forms. Here's another way of looking at the LSTM and GRU units. This is the same as the diagram before, but it writes them out a little differently. For example, we have the sigmoid, and the tan H from before. But this is just another way of looking at them. So they train these. The targets are 3D voxelized, like voxelized 3D models. So just something that you might come up with in SOLIDWORKS. And it uses a rendering engine and takes a snapshot from a certain direction. And it takes a random number of snapshots at different angles in random order. And then it uses those snapshots as the input and trains the output, the target being the 3D models. And so the results are pretty cool. Here's a few of the images that they have. Here's what they decide as like the ground truth, for example. Here's theirs. And this car and others is what they call the state of the art for the single view. And basically what this shows is that their results outperform state-of-the-art methods for single view image reconstruction, which is really cool. Those are really good results. I can, maybe if we had more time, we'd go over the viewer at the end, but yeah. So this graph right here, this is their model. The X is the number of viewpoints that they start adding. That's multi-view stereo. That's the state of the art for multiple images. And as you can see, their network performs better than the state of the art for multi-view until a certain number of viewpoints are added. So the multi-view stereo becomes better once you get, about 20 or so images, somewhere around there. And basically, one thing to mention, they're fairly limited to the voxel size, so the size of these grids. That's, yeah, cursive dimensionality there. But they can't get a whole lot finer. And so that's why the other methods catch up. So this is pretty cool because there's not a great way of combining single view image reconstruction and multi-view. this network, because it memorizes, you can add one image, it gets your result. You keep adding more and more, and you get better results. And so that's useful. And there are a few things I didn't get into earlier on about the texture and sparse versus dense angles, but this is more flexible than some of the state-of-the-art methods. Are there any questions? I can go back and look at results if you are interested.
Very interesting paper. Doesn't this remind you of tomography in a way? Do you know what I mean by tomography, by the way?
I don't.
Oh, tomography is like you take a number of X-rays through a person and you take all of those projections and combine them into a three-dimensional image. It smacks of that.
Right. Except instead of X-rays, it's just external images.
Yeah. And
It's
plus,
a lot of X-rays.
Plus you don't get shadows. You get opaqueness, if you will,
Right.
in terms of your image. Okay. So that is really interesting. It looks like the models sometimes look like Legos. You're making a Lego model of things.
Yeah.
So I'm wondering if Lego could use this as a design tool to make their next Lego model of the Starship Enterprise or something like that.
That would be fun.
Yeah. Okay.
They've got a nice site where you can browse through the results. And so, that's not loading very nicely.
So what are they advertising the application of this as?
They mainly are putting it forward as a tool right now. For example, I mentioned multi-view stereo. They're focusing strictly on developing the tool right now. They might, it's just dealing with image and object reconstruction. They probably assume that since there's such a huge field for it, that there's going to be no lack of applications.
Okay. Well, I'd like to see what they think the applications are going to be. I can imagine, for example, military applications, but even there with things like, I don't know, synthetic aperture radar and other techniques where you can get continuous sort of views of something. I'm not sure.
They don't mention it in their paper. However, if you look at the acknowledgements, Panasonic, I don't know what Baidu is, but Panasonic, that works in electronics and stuff like that, but they've probably got something in the works.
Okay.
That's confidential.
There's something up the sleeve. Thank you, Matthew. Very, very, very good presentation. And thank you for keeping it concise. Appreciate it. Innocent, you are up. Thank you for your patience. And we'll go ahead with your talk now. And please take your time and make sure that it's complete, but concise.
Yeah. Okay. I guess you all can see my screen, right?
Yes, we can see your screen. Yes.
Oh, okay. So the paper I read was kind of a review paper on AGI, like the concepts, state of the art, and future prospects. So this is a paper that was written by Ben Gotzo. So that I'll be kind of talking on kind of the review he did. So the contents would be like first of all, I'll give a little bit of introduction and various ways he talked about characterizing GI, and GI, by GI I mean general intelligence. Then also kind of the approaches so far to AGI, which is artificial general intelligence. Then look into some metrics and environments for human level AGI. So currently, we all know that the AIs or neural networks we have now are kind of designed to be able to achieve a specific task. So looking at this kind of proof that so far is been unsuccessful in achieving the original goal of artificial intelligence. So which the goal was initially trying to like create machines that can be comparable to the intelligence of human. So when you talk about an AGI, you're kind of referring to systems with a broad generalization capability. But the big question arises, like, what is this general intelligence? Trying to like narrow everything down to what general intelligence could be. So the AGI community kind of have some key features they agreed on whenever you're trying to like say something about general intelligence. They have something like general intelligence should involve the ability to achieve variety of goals and variety of tasks in a variety of different contexts and environments. Also, an intelligent system should be able to handle problems and situations quite different from those the creator anticipated the system to do, that is trying to like being creative. So also system should be, and a generally intelligent system should be a good and generalizing, should be good at generalizing knowledge that it gains so as to transfer this knowledge from one problem or context to another. Then another key feature is that humans kind of display the higher level of general intelligence than existing AI programs we have right now. It seems quite unlikely that humans happens to manifest a maximal level of general intelligence. So when it comes to characterizing general intelligence, one of the issues, like I said previously, is trying to like, or rather, the ambiguity of the concept AGI kind of closely relates to the ambiguity of what general intelligence is. So in order to be able to like narrow down these confusions, many approaches have been used to try to like define what it means to be generally intelligent. So some of these approaches, we have the pragmatic approach of characterizing general intelligence. So in this approach, they kind of take human to be the generally intelligent system. So for you to be able to characterize a system to be generally intelligent, you have to like compare that to what a human can do. And before you can say that a system is generally intelligent, that means that system should be able to like take the place of a human being in performing some certain task. So this is kind of the pragmatic approach of characterizing general intelligence. Then when you come down to the psychological characterization of general intelligence, you're talking about characterizing general intelligence, or rather, this approach to characterizing general intelligence also focuses on human-like general intelligence, but rather than looking directly on the capabilities, it tries to isolate deeper underlying capabilities that enable these practical capabilities. So this approach kind of gave rise to ways of measuring intelligence, such as the IQ and the psychological G factor. So, but this approach also gave rise to two concerns. First, which said that while performance within an individual across knowledge domains is somewhat correlated, it's not unusual for skill levels in one domain to be considerably higher or lower than in another. Then the second concern is individuals with comparable overall performance levels might differ significantly across knowledge domains. So the third approach being the cognitive architecture perspective on general intelligence. So when it comes to this approach, or let's say the perspective, that and co in a work that they did in 2009 kind of composed a list in which you can use to like characterize that a system is said to be generally intelligent. And the list is that the system has to have some kind of a fixed structure for all tasks. It should be able to realize symbol system, represent and effectively use modality specific knowledge, represent effectively. So you can just go through the list I have here on the slide to see the features a system has to have before you can characterize it as being generally intelligent. Then you also have the mathematical approach to characterizing general intelligence. So the intuition when it comes to this mathematical approach is that absolute general intelligence can be achievable when you have some kind of an infinite computational ability. Also, some finite computational systems will be more generally intelligent than others. And it can be possible to kind of quantify to the extent they are more generally intelligent than other systems. So under this same mathematical approach, intelligence can be defined as the average reward achieving capability of a system calculated by averaging over all possible reward summable environments, where each environment is weighted in such a way that more compactly describable programs have larger weights. So
could I ask you, it says intelligence is defined as the average reward achieving capability of a system. It seems to me that in order to calculate that, you need to figure out what the reward achieving capability of a system is. And the system itself cannot compute that. That needs to be computed by a human.
Yeah.
So I don't know. There's a number of issues that I have here, but that's one that struck out to me. In other words, the metric for intelligence is defined by a human being. It's kind of self-refuting. By calculating overall possible reward summable environments. That's a lot of environments. And then where does the weighting of the environments come in? That's going to be determined by a human being too also. So it seems like a lot of the metrics applicable to AGI as they're talking about here, or to general intelligence as they're talking about here, have to come from a human being and cannot be assessed by artificial intelligence itself. That's my thought. So
yeah, and from using this mathematical approach, you can also see that, like I said previously, for you to achieve this general intelligence, you have to have some kind of infinite computational ability, which, considering what we have so far, we don't have such an infinite computational ability. So, but one good thing about this mathematical approach is that humans are nowhere near the maximal generally intelligent system, unlike the other approaches that kind of uses humans to like characterize what it means to be generally intelligent. Then we also have the adaptationist approach. This simply means the ability of a system to be adaptable, to adapt to a more general class of environments within a realistic resource constraints.
Innocent, this kind of reminds me, go back to the previous slide, please, just for a second. This kind of reminds me of Russell's paradox. For example, calculating by averaging over all possible reward summable environments. That summation over all possible reward summable environments includes the action of averaging over all possible reward summable environments. And, I suspect that there might be some self-refutation there. I can't put my finger on it right now, but that statement has to be applicable to itself. And what are the ramifications of that? I think that that's an interesting question. And I suspect that it was not addressed by the authors either.
Yeah. No,
okay, please go ahead.
So when it comes to like the approaches to AGI that are applicable right now, you have the symbolic AGI approach. So the guiding principle for all symbolic systems is the belief that the mind exists mainly to manipulate symbols that represent aspects of the world or themselves. So generally, symbolic cognitive architecture focus on working memory that draws on long-term memory as needed and utilizes centralized control over perception, cognition, and action. Although in principle, such architectures could be arbitrarily capable, in practice, these architectures tends to be weak in learning, creativity, procedural learning, and episodic and associative memory. So the most successful symbolic method on learning problems have occurred in the areas of genetic programming, which Koza did in 1992. You have the inductive logic programming and the probabilistic learning methods, such as the Markov logic network. So right by this right side, you can see some other symbolic and cognitive architecture where you have the EPIC, Icarus, SNAPS, and the SOA. So
yeah, if you could go back there, when they talk about these models, are these just theoretical models? I guess one of the comments that I've heard about artificial general intelligence is artificial intelligence is written in Python. Artificial general intelligence is written in PowerPoint slides. And I'm wondering if these are PowerPoint slides with just conceptual ideas on them. And the question is how have these been substantiated by reduction to practice, by using, by giving some different examples and applications? So my question is, do you know? I don't know on these things. I don't know where these come from.
I read so far, I didn't come across where they said it's been kind of reduced to practice. So
okay, are you aware of any place where any of these has been reduced to practice in a productive form?
No.
Okay, go ahead.
So the next approach is the Magentism approach. So this takes the view that higher level, more abstract symbolic processing arises naturally from lower level sub-symbolic dynamics. So the view here is that a more thorough understanding of the fundamental components of the brain and their interplay may lead to a higher level understanding of general intelligence as a whole. So today's emergentist architectures are sometimes very strong at recognizing patterns in high dimensional data, reinforcement learning, and associative memory. But no one has yet compelling show how to achieve high level functions such as abstract reasoning or complex language processing using a purely sub-symbolic emergentist approach.
Great. Okay.
Yeah. Then here are some architectures that follows this approach. The Destin, Sal, Nomad, Sal and Nomad. Then lastly, we have the hybrid AGI architecture. So this is just the combination of the two architectures mentioned previously. So the combination may be done in many different ways, such as like connection of a large symbolic subsystem with a large subsymbolic system, or the creation of a population of small agents, each of which is both symbolic and subsymbolic in nature. So these hybrid architectures are often designed so that they can leverage phenomena arising when multiple components are appropriately connected. So now we talk about the metrics and environments for human level AGI. So when we talk about human level AGI, the problem that arises is how to measure the AGI to know when it has achieved that human level performance. So one can use tests designed to measure human performance, or tests designed relative to human behavior. So the measurement issue then decomposes into two sub-problems. So you have, for you to like quantify the milestone of human level AGI, then also measuring the incremental progress towards human level AGI. So for you to quantify the milestone of human level AGI, you have tests such as the Turing test, the visual world Turing test. So the Turing test, we all know, is the AI, the so-called AI that's kind of was designed to like trick humans. So you have the visual world Turing test. You have the online university student test, where you have an AGI to complete an online, to get an online degree, and in the process should go through every process a human should undergo, such as interacting with the professor, interacting with other students, and every other thing. The same thing goes with the robot university student test, having an AGI to be physically present and in the school structure and go through the school years and get his degree. Then you also have the artificial scientist test, having the AGI to be able to like do his own research on his own. Then when it comes to measuring incremental progress towards a human level AGI, it is not clear how to effectively measure whether one is, let's say, 50% of the way to human level AGI, or 75 or 25%. So, but there are some procedures that can be used to do such measurements, such as passing the elementary school reading curriculum and story understanding. You also have the passing the child and psychologist typical evaluation, which is aimed at judging whether a human preschool student is normally intellectually capable. So I guess this is the end of my presentation.
Okay, thank you. What year was this published, Innocent?
It was published in 2014.
Okay.
Yeah.
Okay, well, we can forgive it. Let me ask you guys this and see what you think. Do you think it's possible for artificial intelligence as it currently stands to take an IQ test?
If it's trained on one.
Yeah, I think it would do pretty good on an IQ test, wouldn't it? I think it would. You know, there's a few things on here. Go ahead and unshare your screen while we talk, Innocent. Yeah, there's a few things that were covered here. Oh my gosh, I could take all day, but I'm not going to. The Turing test is failed, as we talked about. I like the Lovelace test a bit. I suspect that they did not address, for example, in terms of understanding Searle's argument of the Chinese room, and that the idea that artificial intelligence being a computer program will never understand. There's also a materialistic assumption here, and that materialistic assumption is coming under attack. That materialistic assumption is that our mind, our capabilities of creativity, our ideas of common sense, our ideas of understanding are part of our brains. And that the materialistic brain is the source of all of this. I believe that there's growing evidence, although the jury is still out, I must admit, there's growing evidence that that indeed that the mind is external. There's parts of the mind that are external to the brain. There's lots of evidence through neuroscience, neurosurgery, psychology, near-death experiences, I think are compelling examples of this. So yeah, I think that there is that assumption there. If you do assume a materialistic assumption, yeah, maybe you're going to get AGI. The last thing I would mention is if you follow artificial intelligence currently, for example, the projects on Kaggle, where they go out and they give out problems with $100,000 prizes, for example. Those contests are typically not won by AGI, but more specific intelligence. In other words, if you are given a task where you want to win a certain prize, there is literally more human input, human processing, pre-processing of the data before the result is achieved. So it seems that at least in practice, that AGI is going in the opposite direction. It's getting more and more specific, more and more in tune with heuristic inputs. You'll notice that the neural network that Matthew gave, and that there was lots of neural smithing that went into there, wasn't there? There was a lot of human ingenuity that went into setting up the problem to attack the specific problem. And that's what we're seeing more and more and more of that happening, as opposed to going elsewhere. And again, the old idea that artificial general intelligence, in my opinion, is published on PowerPoint, whereas artificial intelligence is written in Python. So time will tell. I think we're going to get more and more clever things. We've seen a lot of wonderfully clever things today here that you can do with AGI, but I still maintain that artificial intelligence will never be creative. It will never be creative, not in terms of the Turing test, but of the Lovelace test. It will never understand what it's doing, and it'll never be sentient. Remember, for example, the example with qualia, the guy biting into the apple and experiencing, I forget what I used, biting into an apple or an orange or something like that, and duplicating that experiment in software. You can't do it. You can't do it. You can explain the chemicals that's going on. You can kind of explain the acidic and an orange flavor and yada, yada, yada. But you'll never duplicate the experience itself. So that is something else that looks like forever will be something which will escape the capabilities of artificial intelligence. So anyway, Innocent, that was very interesting. It was, yeah, it was. I think there was a lot of weaknesses in there, and I think it really showed that the authors didn't dig as much as they probably should have in the opposition of what they were thinking about. Okay, any questions at all, guys?
Is it an appropriate time to ask a slightly tangent question?
Well, maybe a cosine question. Go ahead.
Okay.
I don't know what that means.
Do you think animals have general intelligence?
Well, this is another thing. And Innocent, I'll go back to you. Did they define what AGI was in the paper?
No, they didn't.
See, that's a problem. These are seductive semantics. They are used without definition. Here is what I would define AGI as. AGI will be achieved when artificial intelligence is able to duplicate everything that a human can do. duplicate. Okay, so your question, Matthew, was do you think that animals have what would you say, general intelligence?
Yeah, since it's not technically
So
artificial.
you're using the word define general intelligence for me.
I was just kind of writing off of the general thing, but yeah, I definitely.
Okay. Okay. See, that's the problem is the definition and the use of the seductive semantics. And this happens so much in the AI field where terms are thrown around and really not defined. It is very clear that animals, this is my personal take. Now, I'm not what do they call a zoologist or a animal psychologist or anything, but it seems to me that animals have instincts and that these instincts are born of inbred algorithms. And, does the inborn algorithm correspond to intelligence? I don't know. It's an ant colony getting from the Milky Way bar back to its nest with a little conga line going back and forth. Is that intelligence? Yeah, it is, I suppose, in a way, but really it's following a specific algorithm that allows it to do that. And then we get into those touchy areas that I get in with my wife, kind of dog love. What do you think? Do you think a dog can love? My wife does. Yeah. And so does my daughter-in-law. In fact, I have two daughter-in-laws that believe that animals love. So I don't know. They're certainly affectionate. They certainly simulate love, but does the simulation relate to the true thing? And dogs sacrifice their lives for people. But is this an inbred algorithm instead? Is this the inbred algorithm that substitutes the human master for the alpha dog in the pack? And as a result, the subservient animals must be dedicated to helping the alpha dog survive. I don't know. I don't know about that. So I think it would have to go back to the definition of general intelligence before we could address that. And always remember that when you hear people use these terminologies, these seductive semantics, make sure that they're defining what the heck they're talking about. Okay. And that's fair, right? Like I've defined AGI. I've defined creativity. Creativity is passing the Lovelace test. Okay. We've addressed understanding using Searle's Chinese room. So we have, we've addressed these and we've defined these things, and I think it's very defensible. And if you get out here into a hand-waving, amorphous, sloppy world of semantics, then you can defend about anything. Okay, Innocent, thank you. Any final questions or thoughts? I didn't answer your question, did I, Matthew? But
oh, well, I just had a follow-up one.
Sure.
It's more of a typical, but so if animals don't have this same like out of mind, like they don't have like the mind that we do. They have the brain. Do you think it's possible that this AGI or artificial intelligence could get to the point to be as smart as animals, and then people would be like, aha, we did it? And then it would actually be misleading.
I don't know if you've seen any of the Boston robotics videos where they come out with their artificial dogs that can do incredible things. Yeah, and as far as simulating, I always go back to the great movie Artificial Intelligence, Steven Spielberg's Artificial Intelligence, where that little boy is a robot and he is programmed to love. And you go and you push a little button, and the kid that played that, Haley Osment, I think was his name or something like that, he just stood there, he's like a robot. And then the mother pushed the button and he looked at her, and you just saw love come over his face. Okay. You saw love and compassion for his mother. And was that real? No, he was programmed to do that. But boy, it sure looked real, didn't it? It sure looked real. And his dedication to that love was the topic of the picture. And his dedication to that love stayed on. But I think it was indeed, simulated. It was something that was programmed. And I think that a lot of things can be simulated by AI. I think you can simulate love. I think you can simulate compassion. I don't think you can simulate creativity. I don't think you can simulate understanding. I don't think you can, well, you could probably simulate sentience, okay, with qualia, because you can have artificial tongues, little sensors that grab the molecules out of the air and go, oh, this is blah, 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 must be an orange. So yeah, you could probably do that, but it isn't the replication of the actual qualia. So that's my thought. Now, do animals have this out of mind experience? I think maybe the question to ask there, and again, I'm no specialist, but I pretend to be. So, do they have this out of brain sort of experience? You would have to ask yourselves, can animals be creative? I think that any evidence of creativity is thus far sort of minimal, as far as my experience goes. You're about the monkey, for example, where the bananas are hanging from the ceiling and they leave a stick in the room and he figures out he can take the stick and knock the bananas down. Is that creativity? Yeah, it depends. But all of these things seem to be on the margin that I'm aware of. Now, this would be interesting. Is there a way to test creativity? And this is something I've always wanted to do in AI in order to establish that AI can't be creative, and that is to come up with a test for creativity for AI. And this is stuff that lives on the pages of PowerPoint, just like Innocent's AGI sort of thing. It's something you can talk about, but coming up with something definitive, something testable, something which is has meat to it, is relatively difficult. Okay, well, I can pontificate forever. So any other questions, Matthew? Do you have a follow-up or?
No, that was good. That was really good. Thank you.
Okay, we will see you guys. And thank you for sticking around. Innocent, thank you for doing what you did at the time you did. And Trevor and Matthew, thank you for sticking around. I think that the other people had to bounce because of prior commitments, but this was great. Okay, God bless and take care, and we'll see you at the final examination Tuesday.